Hey everybody, we're going to start looking at power and efficiency and how it relates to work, energy, and momentum in our unit of study here. So oftentimes, like we used force, the F word, incorrectly, we often use work, energy, and power synonymously, but also incorrectly, and that's not scientifically accurate, right? It makes the physics gods very angry. The first thing we'll do is define power in the scientific way, and what power is the rate of doing work. So we know now that work is force times distance, and so we can define power as work per time, and anytime we have rate, there's going to be a time unit involved. So our equation looks something like this. We'll use big P, which is a work per time. Work is also a change in energy per unit time. So that's something to be mindful of when we're looking at these equations. The unit that we'll use is a watt, and that is a joule per second. So those are the units of for power that we're going to be using. So quick examples, pretty straightforward. A physics student setting up a body slam on a biology student. So you lift the 75 kilogram student over the head a certain distance in a certain amount of time. How much power did the physics student generate? So what you first have to do is, obviously we're looking at power, and it is work per time. So we're going to figure out how much work was done. And it looks like we've done this before, but it's the force of gravity times the distance, which is m times g times d. So plugging all those numbers in, 75 for the mass, 9.8 for the gravity, and the distance of 2.2. The work done lifting the biology student is about 16, 17 joules of energy done, right? We're lifting the thing up, pulling it over your head. And then we're given the time, so we'll just plug everything in like so to get 1617 over 0.675. So we get a power value of 2395, about 2400 watts. So that's one way to do the answer, or do the question. Another way we could ask this question, so it kind of adds a bit of a wrinkle, but we're cruising down Wadley. You're at a certain speed, and then you speed up in a certain amount of time, and then you have the mass of the car. How much power did it generate, or we could say was used? Same kind of idea. But remember, so power is work per time, and work can also be classified as the change in kinetic energy, as the work energy theorem says. So I would rewrite this to make it look something like this: 1/2 mvf squared minus 1/2 mvi squared over the time. And that's just showing me how that changes. I'm going to write it kind of in a factored form, makes things a little cleaner to use. 12 squared minus 4 squared. It's just my kinetic energy factored. When I crunch my numbers, I get about 12088.9 watts used, right? You can also say a joule per second, but this is the better way to do that. All right, so we have a couple of examples on how power works. These are generally not crazy difficult. Another useful equation can be derived. So I know that power is work divided by time, and I know work is a force times distance over time. Well, if I take a look at my distance over time, well, that's velocity. So the other useful equation for power is force times velocity. And that's particularly useful when I have something that maybe looks like this. I'm pushing your big clump of physics homework up a ramp. So the first thing I'll do is I'm going to sketch the diagram in the little box here. There's not a lot of room to work on this, but here's my object. And so all of that stuff that we worked on, it's still going to come back to haunt us. I have my weight pulling down. I'm going to pull my friction force. It is going straight that way. And it looks like I'm pushing up the ramp. I'm going to call that F sub P. I'm going to have my parallel force going this way and my perpendicular force going this way, knowing that angle remains the same. Now, one of the keys to this question is remembering that this is moving at a constant velocity. So sometimes the object will accelerate, and that makes it a little more fun to do. But here we know that the net force is going to be 0. So I'm going to go ahead and call up the ramp positive and down the ramp negative. That means I have the pushing force up the ramp, friction force pointing down the ramp, and that FG parallel going down the ramp equals to 0. So rearranging this, I'm going to go ahead and write this in the form that I need. So now I can figure out what my pushing force is, and that's going to be important. I probably should have said this at the beginning, but what I'm going to end up doing is using my force times velocity to get how much power I'm using here. So I know what that velocity is. Problem gave it to me as 3.2. The F here is going to be the FP. So I probably should have rewritten it to indicate the correct variables. When I crunch my numbers here, I get the pushing force is about 114.2 newtons. So check my math on that, make sure that's right there. And then when I plug everything in, power is that FP, that 114.2. The velocity was given to me at about 3.2. So my power required to push your stack of physics homework up the ramp is about 365 watts. Cool. Another main idea that we want to talk about is the efficiency of things. And this is kind of, one of those real world examples. Nothing is 100% efficient. We have a lot of energy that is lost due to heat and friction. So it's getting cooler out, so we're going to use electric heater sometimes. Electric heater is about 95% efficient when we look it up. A car is generally 30% efficient. An old school incandescent light bulb, I don't know if we even have those anymore, but it is about 10 to 20% efficient. I looked this up earlier because I was curious. I found a little website that has a couple of things here. But an LED light bulb, which most people are buying these days, is only about 40 to 50% efficient. I'm not sure if that's right. I might have to do a little more research on that. But all of these percentages seem kind of low, but anytime you use energy for any reason, you have a lot of loss that's generally due to heat and or friction. So obviously a car generates lots of heat, lots of moving parts. Even electric cars, they generate some heat. People's body temperature is really interesting. The byproduct of all of the metabolic processes that go on results in a body temperature of about 98.6 degrees Fahrenheit, which is kind of cool. But one of the things we're going to do is we're going to calculate things, and we're going to look at different ways to calculate the efficiency. One of the first things we'll do is we'll look at the work in versus work out, multiply it by 100 to get the efficiency that way. The other way we'll look at it is the power in versus the power out, multiply it by 100 to get the efficiency for whatever processes we're looking at. One of the things to be careful of, or the trickiest, I guess, is figuring out which is in, which is out. That's one of the trickier parts about working on these questions. One of the things you have to know that the work or power in is always going to be greater than the work or power out. We haven't figured out how to make things more than 100% efficient. That'd be really cool if we could figure out. But let's work a couple of questions here to see how we can use this power and efficiency idea. So basically, this question was a little bit more elaborate, but I kind of whittled it down to the basics. You have a mass of 2,800 kilograms and is raised 120 meters. The first thing we're going to do is calculate the amount of work done to raise it. And really what's happening is it's like a theoretical value here. So let's figure out what's going on here. So part A, it looks like the work is going to be the force times distance. It's also the change in energy of the system. And so I've raised it from a zero height. So I'm going to use the potential energy here. So it's raised mgh. So it looks like work is going to be 2,800. There's the mass. Gravity is 9.8. And I've raised it about 120 meters according to this question. So I get a work value of about 3.29 times 10 to the 6 joules. And so remember, this is a theoretical value. All right, we might have to use that here in a little bit. In reality, the object accelerated from 0 to 193 kilometers per hour in 3.8 seconds. Let's figure out what the actual power input was to make that thing happen, to make that process happen. First thing we need to do, everything needs to be in meters per second. So 193 kilometers per hour is 53.6 meters per second. Make sure you understand how to do the conversion. The work done, in this case, is the change in kinetic energy in the system. And it started from rest. And so it only has a final, so I'm just gonna go ahead and use 1/2 mv squared. If you're kind of getting confused on where that's coming from, let me know and we'll hopefully we can clear that up. So the work done on this is 1/2 mass of 2,800. That final velocity is 53.6 squared. So the work done to get it going is about 4.02 times 10 to the 6th joules. It wanted the power, so all I gotta do is figure out what the time unit was, and it was 3.8 seconds. So 4.02 times 10 to the 6th divided by 3.8 seconds. So I get a power input to get this thing moving as fast as it was of about 1.06 times 10 to the 6 watts. And so that is power in. I'd like to make sure I keep everything in order here. And then this last part was determine the efficiency from start to end. So part C, let's plug it in over here. So for part C, basically I'll kind of use this efficiency as the work out over work in. So my work in is I'm going to go ahead and use this theoretical value right here. That 3.29 times 10 to the 6th value. That was the work in, that was joules. The work in is this value right here. So I'm going to go ahead and grab that value. That's 4.02 times 10 to the 6th joules. Multiply that by 100 to get my percentage, how it works. So the efficiency of this particular process is about 82% efficient. So not awful, but also, pretty far from 100 if you're looking at that kind of thing. All right, so now let's take a look at the next question. Our last example has a roller coaster being launched up a hill. It goes from 0 to 64 kilometers per hour in about 2 seconds, and it has a full mass. So one of the first things I'm going to do is I'm going to try to convert as much as I can. Looks like 64 kilometers per hour is 17.8 meters per second. I have the mass and I have a distance that it travels up, so it looks like there's some kind of change in energy going on also. So the first thing we're going to do is look for the power output from the ride. In other words, what all happens. So power is equal to work divided by time. I first have to figure out what the entire output was of the ride. There is a change in kinetic energy, and there is a change in potential energy. So this is 1/2 mv squared. It started from rest, and then it raised itself a certain height. So I'm plugging all that values in. So the rest of this is just plug and chug. So my values for this should be, hopefully I did the math right, 7.1 times 10 to the 5th. This is 1.5 times 10 to the 6th. So I get about 2.2 times 10 to the 6th joules worth of work done. For the power, divide that value by time. And in this case, it took 2 seconds for all of that to happen. So I get about 1.1 times 10 to the 6 watts, right? And so remember, this is work out and power out. Those values are going to be important later on when I start trying to calculate the efficiency. Part B tells me that the power consumption during the initial launch is about 1.45 megawatts. So 1.45 megawatts is times 10 to the 6th watts, okay? And this is the power in. That's what I had to plug into the ride to make it do its thing. So to take a look at the efficiency. So the efficiency is going to be the power out over the power in. So it gave me my 1.45 megawatts. And the power out is about 1.1. Multiply that by 100. So when I get that, I should get about 76% efficiency from the ride. Cool. Part C tells me something about the heat. And so we talked about how things getting lost due to heat is kind of interesting. The energy due to heat is going to be all of the energy in the initial part minus the energy of the final, and so obviously that final part's going to be less. So for me, this initial energy piece came from all of the work out done right here. So I already kind of figured that out. I don't have to calculate that again. So the initial energy for me is about 2.2 times 10 to the 6th. That final energy, I'm going to be able to figure out by 1/2 mv squared. And what happens here is it's telling me that it's pulling in at 8 meters per second. So that's kind of what it starts, and then it ends up stopping at some point. So what's happening is it's not moving as fast as it should be because some energy was lost due to friction. So we're going to plug that in here, times 10 to the 6 minus 1/2. My mass is 4,500. Here's my velocity. So the energy loss due to heat, once I crunch my numbers, is about 2.06 times 10 to the 6 joules. I'm just going to make a note here, lost to heat, right? He was going slower than he should have. So the last thing we're going to figure out is what is the force required to stop this, making sure you have the right kind of brakes or something like that. Work is, so basically it's hidden in work. So I know work is force times distance, and what the work generated is the change in kinetic energy. So work is going to be the final kinetic energy minus the initial kinetic energy. And I guess I could have changed this here to say force times distance, looking for the force value here. I know the thing comes to a stop, so there's no final kinetic energy. So the equation that I would end up looking for at the end looks something like this. The initial kinetic energy, negative 1/2 mvi squared, over the distance, oh wow, can't keep things straight today. Force divided by distance. And that should give us what we're looking for. So I have the negative 1/2, the mass is 4,500. The initial velocity as it's rolling in is about 8 meters per second squared. We're dividing the distance of 2 meters. So when I crunch my numbers, I get a force of 7.2 times 10 to the 4th newtons. I'm going to say in the negative direction. Right, so it was hidden in here. And since they're braking, right, it's brought to rest, that means obviously the brakes are pushing it in the other direction. But that is a quick rundown of how all of this kind of ties together. All right, thanks for watching. If you have any questions, let me know. Talk to you later. Bye.